There you go.
Okay, I'll start. And since I have a slide about me, so I will directly share my screen. Okay, is it visible?
Yeah.
Okay, so first of all, thanks for inviting me to have this talk about my CIKM paper entitled Do Graph Neural Networks Build Fair User Models? Assessing Disparate Impact and Mistreatment in Behavioral User Profiling. This is a joint work with Ludovico Boratto and Ernesto William De Luca. And as I already said, this was presented at CIKM 2022 at Atlanta in Georgia. Being a short paper, it has been presented as a poster, and I also leave you a QR code for reading the entire paper, where you can find all the references I will mention. Okay, a bit about me. I'm Italian and I had my master's degree in computer engineering at the University of Naples, as well as a second level master degree in artificial intelligence at the University of Turin. While doing the master degree in artificial intelligence, I worked as a technical leader in a company called Blue Reply. And currently, I'm a PhD student and a research and teaching assistant at the Otto von Guericke University Magdeburg in Germany, and a research fellow at the Leibniz Institute for Educational Media based in Brunswick in Germany. And since 2021, I'm also adjunct professor in software engineering at the University of Rome Guglielmo Marconi. I would like to start from the main finding of my paper, and then guide you towards the path we followed to reach it. And this is the main take-home message of our work. It's that different user profiling paradigms in graph neural networks models affect fairness result. I will start from the background. So nowadays we are overwhelmed about interaction with social networks, recommended system, information retrieval systems. And this interaction create a huge amount of personal information and personal data shared intentionally or not on the internet. To this aim, the user profiling is the main field that takes care about this topic. And in particular, user profiling aims to infer individuals' interests or personal trait or in general user characteristics from this generated data to create an efficient representation that is usually called a user model. A user profiling can be divided in explicit user profiling, where data comes from online forms and surveys. And so these are static characteristics retrieved from users. But modern systems are more into the implicit user profiling, where data is based on individuals' actions and interactions that are behaviors. And so all these topic or this subfield is also called behavioral user profiling, and in particular it's what we are working on to model these behaviors of the users. The graphs are a natural way where each node of a graph represents a user or an item, and an edge represents the interactions between them. In this view, the graph neural networks raised in the last few years as a perfect solution to handle with the behavioral user profiling. what happened in general in user profiling is that the approaches, no matter, so the image is a neural network, but also general machine learning algorithms for user profiling are usually assessed as a classification task where the system is required to correctly classify a specific user characteristic, such as gender or age or salary or whatever, depending on the context, the data set, and so on. Going into the specific of the graph neural network, we know that as any machine learning system trained on historical data, also these technologies are prone to learn the biases in such data and reveal them in their output. Furthermore, GNNs are proved to also amplify these biases and discrimination due to their topology, because as you can see, as you know, in a graph, of course, nodes that are close to each other are more prone to influence each other. So these, with a training, with a graph neural network, can create amplified bias in the output. In this slide, algorithmic fairness is one of the key topic in computer science. And at the time of this paper being submitted and then published, there were no assessment of fairness for GNN per user profiling models. And so the contributions of our paper, we performed 2 user profiling tasks. So as I said, 2 classification tasks, basically by executing a binary classification on 2 real-world datasets, leveraging the most performing GNNs for user profiling. I'll explain all the models, the real-world datasets later on. We assessed for the first time in literature disparate impact and disparate mistreatment, and I also gave a definition in the next slides. For graph neural network, designed specifically for behavioral user profiling, and we consider 4 algorithmic fairness metrics. And from our set of experiments, we derived 3 observations and the main take-home message that I already illustrated. The main goal was to try to correlate the different user profiling paradigms of the 2 GNNs with the fairness metrics scores. So we tried to derive this correlation through the following research question. How do the different input types of the analyzed GNNs and the way the user models are constructed affect fairness? To what extent can the user models produced by the analyzed state-of-the-art GNNs be defined as fair? That's also important. And going forward, we also asked if the usual and the common disparate impact metrics, if they are enough to assess the fairness of GNN-based models in behavioral user profiling tasks, or if something else is needed. And in particular, we exploited the disparate mistreatment metric. Okay, going through the analyzed models. The analyzed models the models we analyzed, are CAT-GCN and RHGCN. This is the architecture of CAT-GCN. I also leave you the reference. And CAT-GCN is a graph convolutional network that is that is tailored for graph learning on categorical node features, as the name suggests. And this model enhances the initial node representation by integrating 2 types of explicit interaction, modeling into its learning process. The second architecture is RHGN. RHGN stands for Relation Aware Heterogeneous Graph Network, and it's designed to model multiple relations on an heterogeneous graph between different kinds of entities. I emphasize these multiple relations because it will be very important when we analyze the results. I repeat, cat GCN is just, sorry, one type, create one type of relation in two ways, with a local pairwise interaction and a global feature graph-based interaction, while RHGN creates multiple model multiple relation on the input heterogeneous graph. Talking about the
Sorry,
algorithm.
can I ask a quick question before you continue? I'm not familiar with these particular architectures, so I just wanted to ask a few questions to make sure that I understand.
Yeah.
So the I guess my question is like, what is the difference between a graph neural network that is specific to user profiling from a graph neural network that is like kind of canonical to the recommendation setting? It seems here like you might, it seems like you use a bipartite graph here as well, or am I wrong?
Yes, and I would say when I said it's specific for user profiling task, it's mainly because their original evaluation, their application is based on user profiling task. They have been not evaluated on different contexts. And in the original paper, they specify that the aim of building this, specifically for cat GCN, the aim of building this particular architecture was for the user profiling tasks. If you see in here is also an important part where they rely a lot this node representation, so the result of the node representation. But I agree with you, if the graph, the original graph contains only items, for example, this architecture can be used as well, but has been not demonstrated to be effective as well as on user profiling tasks.
Oh, okay, gotcha. Thank you so much.
Okay, about the algorithmic fairness, we applied two kinds of metrics. As I said, disparate impact and disparate mistreatment. Disparate impact refers to a form of indirect and often unintentional discrimination that occurs when practices or systems seem to apparently treat people the same way. And this family of metrics concern with situation where the model disproportionately discriminates against certain groups, even if the model does not explicitly employ the sensitive attribute to make prediction, but rather on some proxy attributes. And this is exactly what happens in the analyzed graph neural networks, where the user models are created by aggregating information from neighbors, and the sensitive attribute is not explicitly taken into consideration into the classification. About disparate impact, we used three metrics. Statistical parity, also known as demographic parity, defines fairness as an equal probability for each group of being assigned to the positive class. So basically the predictions should be independent with the sensitive attributes. Equal opportunity requires instead that the probability of a subject in a positive class should be classified with the positive outcome, and this probability has to be equal for each group. I forgot to mention that in this work, we are talking about group fairness, not individual fairness. Maybe it's needed. And the third metric adopted for disparate impact is the overall accuracy equality, and it defines fairness as the equal probability of a subject from either positive or negative class to be assigned to its respective class. Basically, each group should have the same prediction accuracy. What I'm showing in the slide, it's not the original definition for each of the metric, but rather it's the difference between the two members of the equation to create a score to evaluate to quantitatively evaluate the metric, the fairness, sorry, of the graph neural networks model. Basically, the original form, for example, for statistical parity, says that the probability of the output equal 1 given the sensitive output being 0 is equal to the probability of the rest. Sorry. For disparate mistreatment, I'll specify a thing that there can be some scenarios where it is hard to define the correctness of a prediction related to sensitive attribute values. If you think, for example, as in some user profiling task, we can classify the consumption level on an e-commerce. In this case, it's impossible to understand what is the positive class. If we binarize this consumption grade, we cannot say that 0 or 1. 0 is more positive than 1 in this situation. Different in other contexts like hiring, not hiring, or conceding a loan, granting a loan or not. And in this context, comes disparate mistreatment, and we argue that a complete fairness assessment should always include this metric, this family of metric. That the disparate mistreatment considers the misclassification rates for user groups having different values of the sensitive attribute instead of considering the correct prediction. This notion is significant also in contexts where misclassification costs depend on the group affected by the error. So the error on each group is, the cost of the error on each group is different. And for this category, we chose the treatment equality. This metric requires that the ratio of errors made by the classifier has to be equal across different groups. That means that each group should have the same ratio of false negatives and false positives. Now the dataset adopted. We adopted 2 real-world datasets. The first is Alibaba, that contains click-through rates data about ads displayed on Alibaba's Taobao platform. And we choose this one also because it's been already adopted in both CAT-GCN and RHGN original paper. Of course, to make the experiments comparable, we had to slightly modify the dataset, and you can find all the details in the experimental settings section of the paper. The second dataset is called JD, and it consists of users and items from the retailer company with the same name. So it's again an e-commerce dataset having click and purchase relationships. And this was used in RHGM as well. Here, there's 2 tables describing the dataset characteristics and the distribution of label and sensitive attributes values. You can see that in table 2, class 1 and class 0 are not always balanced. And we did it on purpose also to evaluate how the 2 models act depending on how not how balanced or not is the data set they are working on. Also something to specify, this sensitive attribute is called bin age because the original data set has 7 classes on Alibaba and 5 classes on JD, so 5 ranges and 7 ranges for the age. But as it is common and usual for algorithmic fairness, since the metrics are almost all binary, we binarize the two classes, so for both data set, and we choose the gender as the target class and the age as the sensitive attribute in all the experiments. So the experimental settings for the first research question, we considered the disparate impact metrics, so the statistical parity, the equal opportunity, and the overall accuracy equality. And we compared this score between the two graph neural networks to measure the model's discrimination and evaluate the different user profiling paradigms. For the second research question, we compared and contextualized the values of statistical parity and equal opportunity with the result of FAIR GNN. FAIR GNN is another recent framework for adopting graph neural network for user profiling tasks, but directly it has an additional component to create fair results. In their paper, they adopted statistical parity and equal opportunity to evaluate the fairness of the experiment. And what do we mean with contextualize the values? So we took the score of FAIR GNN as ideally, also knowing that the lesser the better, a result of our metrics. If it's not clear, please ask, because I realized that probably this sentence was not so clear. And for the third research question, we extended our fairness evaluation, as I explained before, to consider the treatment equality and to determine to what extent the graph neural networks model discriminate against user from the perspective of disparate mistreatment in comparison to the disparate impact. Going to the results table. In this big table, you can see the comprehensive result of all our experiments. For each row, we show the data set used, the label. The label is the target class, the model adopted, and then 3 performance scores: the accuracy, the F1 score, and the area under the ROC curve, and then the 4 fairness metrics. As you can see, for both data sets and in all the experiments, the pattern of the result has been almost the same. So for the accuracy part, RHGN performed better, and the main aim of this performance part was at the beginning to confirm that our experiments were in line with the results of the original papers, and we find the same result. So also in their original papers, LHGN outperform CAT-GCN, even if for F1 score and the area under ROC curve, the results are slightly worse for CAT-GCN. Then for all the fairness metrics, the results are better for LHGN in every settings, for every fairness metrics adopted. From these results, we derived the first two observations. The first one saying that the ability of RHGN to represent users through multiple interaction modeling gains better values in terms of fairness than a model only relying on binary associations between users and items, as CAT-GCN. This is the reason why I emphasize the multiple relation thing while describing the RHGN architecture, because from the result, this is one of the conclusion we came to, because it is really better, and there's no, in all our experiments, there was no possibility for CAT-GCN to be better on fairness metrics than RHGN. So one possible explanation is written in this observation. Anyway, through the comparison with the fair GNN results, we came with the second observation. And so even though RHGN demonstrated to be a fairer model than CAT-GCN, we argue that the debiasing process is equally needed for both graph neural networks. And this means that the single results of RHGN is not that good as the current state-of-the-art graph neural networks for working on fairness. And so in this comparison, one model is better than another, but for 3 of the 4 metrics, in particular, equal opportunity, overall accuracy equality, and treatment equality, also RHGN is not fair in a broader sense. This broader sense, I repeat, comes from the comparison with the results of fair GNN. Now the third experiment. In this experiment, we computed the variations in fairness score between CAT-GCN and RHGN. I recall that what we were trying to find was an explanation, or an explanation about whether it's needed to go beyond the common fairness metrics, so the disparate impact, statistical parity, and equal opportunity. And what we found in computing these variations for each combination of metrics and dataset and GNNs is that, the bigger variation is displayed for the treatment equality. And for that, we came to our third observation. So in scenarios where the correctness of a decision on the target label with respect to the sensitive attribute is not well defined, as our case, or where there is a high cost for misclassified instances, not our case, a complete fairness assessment should always take into account disparate mistreatment evaluation, because in our case, with this extensive set of experiments, we found that is the most problematic part. So the misclassification rates in this assessment has been more problematic than the correct prediction in terms of fairness, of course. So to summarize this presentation, we conducted for the first time in literature a fairness assessment for GNN-based behavioral user profiling models. And our analysis on 2 state-of-the-art GNN models, 2 real-world datasets covering 4 algorithmic fairness metrics, showed that directly modeling raw user interaction, and it's the case of CAT-GCN, with a platform hurts a demographic group, meaning it's unfair, who gets misclassified more than its counterpart. In future work, we will explore other aspects of fairness analysis in this context. For example, a multi-class and multi-group perspective, This is done basically for what we were talking at the very beginning of this call. We found some ethical implication. So we studied the ethical implication of this kind of metrics, and yeah, it's already accepted. So I can tell you, in bias workshop at EKIR, we will present this paper to at least give our vision about this problem, because the binary classification can create a real distorted vision of the context of user profiling. And so we are trying to go towards a multi-class and multi-group fairness analysis. And in future, of course, our aim is also to introduce some novel procedure for bias mitigation, probably directly for multi-class or multi-group perspectives. Thank you for your attention, and these are my contacts. You can contact me via email or on my Twitter account, and I leave you also my website.
Thank you so much, Erasmo, for your presentation. I open the floor for other people to ask their questions first, as always, and then I will follow up with my own. Does anyone have any questions?